Hey guys, in this video we're going to be talking about the chirality and the Fischer projections. We're not going to be specifying the configurations of the chiral carbons in this video because that's out of the scope of introductory chemistry course. We're just going to be focusing on how to determine if you have a chiral center or a achiral center. Okay, so let's suppose I have a carbon here, and for something to be a chiral center you must have four different groups or the atoms attached to the carbon. Now I can clearly see here in this carbon I got four different things because I just colored those with different colors. So assume this pink color is different, the green, this brown, and this gray, they're all different groups around the carbon. So that's what makes this particular carbon at the center a called chiral carbon. Okay, and if it's not the same, if you have at least two groups to be the same, then it's not going to be chiral, and sometimes you call that achiral. Okay, what about this second example I have posted here? Now in the second example I have actually the atoms in there or the groups in there rather than just the colors. So then you want to look at individually. So if you look on the top, there is a hydrogen. If you look on the bottom, there's a chlorine. So obviously so far this hydrogen and chlorine, they are different. And then what about the left side? The left side we got this CH3 group. So don't look at only the first atom. So if you look at the first atom, you will say, okay, there's a carbon there. And when you go onto the right side, there is a carbon there as well. And someone may like, okay, they are the same, so they may not be the chiral. No, that's not how you look at it. You have to look at the whole group. So when you look at the whole group, of course, this CH3 is different than the hydrogen and the chlorine, and then this CH3 is also different than this CH2 CH3 group, which is going to be your ethyl group. So this is your ethyl group. This CH3 would be your methyl group. So as a result, this is going to be the chiral carbon. Okay, what about this next one? Well, it's probably going to be a good test for you guys if you can pause the video and figure out how many chiral centers you got in there. Okay, so assume you did pause the video and figured out the chiral centers, and now let me tell you how many are there. And if it becomes hard to figure out how many are there, you may have to look at every single carbon one by one. If I give you an example, if I focus on this very first carbon, and then I go like, okay, well, there's got to be three hydrogens to make the total of four bonds because it's a skeleton structure, and since you got three hydrogens around it, it's not going to be chiral. You have to have four different atoms or group of atoms attached to those carbon to make it chiral. So the first one is not chiral, so I'm just going to erase that. Okay, what about the second one? All right, so when I focus on the second one, I see three bonds there. That means the fourth one must be the hydrogen. So you want to go ahead and put that in there when you're trying to learn it. Once you get a hang of it, you may not have to draw the fourth bond or the hydrogen there. Okay, so I see this OH and this hydrogen, they are obviously different than one another. Okay, what about on the left side? So on the left side there is one carbon, so I can say there is going to be like a methyl group, so that's different than what you're going to have on the right side. So this whole group on the right side and this methyl, they are different than one another. So since they are different than one another, this particular carbon is indeed going to be your chiral carbon. Okay, what about any other centers, chiral centers in there? Let me change the color there. Okay, what about this last one here? Not last, the second last carbon here. It's kind of in a very similar scenario than this second carbon that we just talked about. We got an OH on the top. It's missing the fourth bond, so that means it must be the hydrogen. So we got the hydrogen, we got the OH, and then we have the CH3 on the left side. So that's different than the hydrogen, the OH so far. And then you got this group on the right side. And then you got this group on the left side, rather, that's going to be different than what you have circled in the green so far. So that's also going to be your chiral center. Okay, do you see anything else there that's going to be chiral? Well, some people may argue that, what about this carbon right there? And it's worth a shot looking at it. So you have a methyl group on the top, all right, so that's different. And then the fourth bond is going to be coming from the hydrogen there. So that's different. So this CH3 and this H, they are obviously different than one another. But what's going on to the right side and the left side? All right, so this structure kind of looks very busy right now because I made all those circles. And I could probably erase some of those. Just kind of make things look a little bit better. What about the left side and the right side? Okay, so don't just look at one atom, just look at the whole group. When I look at this group right there, and when I look at this group right there, are they different than one another or the same? Well, they look very similar to me. There is a CH2 there, CH2 there, and then after that you got a carbon with the OH and the methyl group. Same story on the right side. So that as a result, it may seem like this carbon right there that's in the pink color, it originally may seem like it's chiral, but it's actually not chiral. The group on the left side and the group on the right side, they are the same. So it's going to be achiral. And the only centers you really worry about is the chiral centers. All right, so make sure you're able to identify your chiral centers. So if I have a chiral center, then there are usually two ways you can express that chiral center. Okay, so for example, what if I take, let me just copy this down. What if I just take this molecule right there and copy this down here? And I'll show you what are the two different ways you can put it together. So I'll erase some of that. If I put a mirror in front of it, so let's say I got a mirror right there. So when you have a mirror, what you see outside the mirror is going to be the reflection of that. And I can copy this down again. So when I see the reflection, the only things that's really going to change is actually this. Oops, probably erase that. The only thing that's really going to flip the positions is going to be your gray and the green ball there. So your gray ball is going to be right there. Alright, so then you can shade this. And then your green ball is going to be on the other end right there. So those are the only things that's really going to change there. So those two different structures that you just got, they have the same connectivity, but their spatial arrangement is different. And there's no way you can rotate, let's call this A and let's call this B. There's no way you can rotate A somehow to get the B. That's not going to happen. So as a result, they are actually going to be called configurational isomers. So remember, the configurational isomers, their spatial arrangements is their connections are the same, but their arrangements are different, so that you can't go from one to the second one just by rotating the bonds. And to be more specific, these configurational isomers are actually called stereoisomers. And these particular ones, when you have one mirror image of the other one, they're going to be called the enantiomers. So these two are going to be the enantiomers. A good example of an enantiomer is going to be your hands. When you put your right hand in front of the mirror, what you see on the other side of the mirror? Yes, the left hand, because the shoes is another example. Your right shoes and the left shoes are not the same. They are the mirror images of one another. If I take example of glass, the glass in one set of glass, if you pick one pair where the two glasses, they are going to be the same. They're not the mirror images of one another. They are going to be superimposable on one another. But when you talk about your left hand and right hand, they are mirror images of one another, and they're not superimposable on one another. So what that really means, what the superimposable really means, if I just roughly copy this down, and if I try to put it on the top of this, I don't really get the same structure because of this green and gray are flipped. So that's what this non-superimposable means, that they're not going to be overlapping right on the top of one another. The same story with your left hand and right hand. So try putting your left hand on the top of your right hand. Your thumb is going to be in the different directions, all right? So that's what makes it non-superimposable. Okay, so I'll probably just cancel that. Okay, so one of the easier way to kind of express these chiral centers is via Fischer projections, especially when it comes to the sugars. All right, so let's talk about how you're going to be drawing the Fischer projections of the sugars. So in a Fischer projection, you're going to have a vertical line and you're going to have a horizontal line. And typically, when you're doing the sugars, your aldehyde or ketone is going to be on the top. So I'll just, in this particular case, I'll just put in the aldehyde here. And then you're going to have your CH2OH group on the bottom, and then your hydroxyl group and your hydrogen is going to be either on the left side or the right side. So let's say if I have this on the right side, the OH, then this is going to be on the hydrogen is going to be on the left side. So that's a typical presentation of the sugars when it comes down to putting them in the Fischer projection. Okay, so then what's this going to be called? It's got 3 carbons, 1, 2, 3. All right, so since it has 3 carbons, it's going to be called a aldo triose, because 3 carbons and aldehyde groups and aldotriose. And since the OH here is going to be on the right side, it's going to be in a D sugar. Okay, that's the only chiral center you have in this particular sugar molecule. Now, what does those lines really represent? All right, so I'm going to write those down here. So if you have a line that's in a horizontal line, so these lines, they actually are coming out of the page. And that's your horizontal lines. And then your vertical lines are going to be going back into the page. So that's an important thing to understand what those horizontal and vertical lines represent in the Fischer projections. So what that really means, if I want to redraw it based on what I just said, I would have this OH group coming out of the page. So this is how you show something coming out of the page with a solid wedge. And then I will have the same story on the other side with the hydrogen that's coming out of the page. And then your vertical line is going to be going back into the page. So that's how you're going to be representing those. So you got the aldehyde group on the top, and then the vertical line going back into the page on the bottom as well, CH2OH. So that's how you're going to be representing the Fischer projections. And it's just very easy to picture the different types of isomers you're going to be seeing when you have the Fischer projections drawn out. Okay, so let me show you why it's actually easy to picture the Fischer projections when you're trying to determine the different types of stereoisomers. So let me copy this down here and erase part of that. So if I draw a mirror here, so suppose I got a mirror right there, then what you're going to be seeing on the other side. Well, let me just copy this down. Okay, so everything else is going to be the same. The only things that's going to be flipped is the position of your OH and the H. So whatever is closer to the mirror is seen closer when it's inside the mirror as well, or another way of saying they are going to be the mirror images of one another. So the OH is going to be right there, so keep that in mind. That's going to be the closer group. And then your H is going to be furthest away. All right, so then those two, since they are the mirror images of one another, the relationship between those two is going to be the enantiomers. So it's a stereoisomers, and indeed it's a configurational isomers, but to be more specific, it's going to be an enantiomer because they are mirror images of one another. Okay, how would you really call this first one and the second one? Now the first one, I know it's going to be a D sugar, so it's a D aldo triose. because the OH is on the right side. That's what determines whether it's going to be in a D sugar or an L sugar. Now, when we look at the second one, now all of a sudden your OH is on the left side. So since your OH is on the left side, this particular sugar is going to be called an aldose. Okay, so that's going to be the difference between the enantiomers. One is going to be the D, the other one is going to be the L. All right, so here, this is how you're going to be representing your Fischer projections, and this is how you're going to be trying to figure out the enantiomers. I'll talk about the enantiomers again in another video where I have talked about the diastereomers, the apomers, and the mesos, and the enantiomers. Hopefully this was helpful. If you have any questions, feel free to leave the comments in the section below.